Alright, and welcome back everyone. In this video, we're gonna go over variable area transport. So far, we've been dealing, if you've been following the playlist, we've done problems in Cartesian coordinates. We've been looking at very flat surfaces. We've been looking at flat sheets, flat membranes, so everything has been flat. But as you move on to cylindrical coordinates, your area of transport, the area of the area varies with your radial position. The area of transport varies with radial position in both cylindrical and spherical problems. Okay, we'll explore that in another video. For this video, we're just gonna look at a axial heat conduction problem. And the problem that I'm gonna go over is adapted from the first volume of Brodkey and Hershey. Please refer to the bibliography, and it's an adaptation of a solved example. So, okay, I'm gonna leave this up there for a second, pause the video, and give this problem a read. Okay, very good. I'm assuming that you guys have read through the problem. So let's see. The diameter of a cone linearly varies in the z direction. So here I have at z equals 0, I have d naught, and on the other end I have d sub l. So my diameter is varying, and if the diameter of the cone varies, that means that the cross-sectional area is varying. No heat transfer. Okay, no heat transfer in the radial direction. The heat transfer, we're only dealing with one directional heat conduction, and that is in the axial direction. Okay. So we have, as you can see, we have a temperature difference. We have at z equals 0, we have temperature T1, and at z equals L, we have temperature T2. So that temperature difference along the different axial lengths is going to drive the heat transfer. Now we got to calculate the steady state heat transfer. Steady state. Okay, that's going to make my life so much easier. Assume constant conductivity. So far, okay, let's see what we can start off with. Let's start off with the diameter part. The diameter is varying. So if I want a function, if I want my diameter as a function of z, it's gonna take the form of y equals mx plus b, as you can see from the schematic and as it has been mentioned in the problem. So I'm just gonna use a very simple linear interpolation. The diameter at z is gonna be equal to the difference in the diameter, dl minus d0 over L minus 0, that's the slope, times z, okay, z minus 0 plus d sub 0. And that's the result I get. That's my function. Okay. Alright, I'm just gonna, this right here is my slope. I'm just gonna call this delta d, the change in diameter over the change in length. So that's gonna be my slope, plus times z, of course, my independent variable, plus my, so at z equals 0, if I plug in z equals 0, I'll get the initial diameter, so that's good. All right, so now I have my relationship. This relationship gives me my diameter at different axial lengths, diameter at varying axial lengths. I'm just going to scribble that, varying axial lengths. But now, okay, because the diameter is varying, the area is going to vary. Okay, I already know that. I can tell that that's just some common sense. So the cross-sectional area along the axial length is going to be a function of z. And it's going to be equal to pi over 4 at a given. So if at z equals 0, your cross-section is going to be smaller compared to the cross-section at midway. Okay, and as you go from z equals 0 to z equals L, your cross-section, the size of your cross-section is becoming bigger. Okay, so if I were to show you this in 3D, so this is where you're starting off with, this is somewhere in the middle, and as you go along, so your cross-section is increasing. Okay, so how can we, each of this at any given point, the area is the area of a circle, so that's just going to be pi over 4 d squared. okay, and I know the functionality. I know how my diameter is varying with respect to the axial length. I know how my diameter is varying with respect to axial length. So combining these two, I can get, hold on, I can get my expression for the variation of area with respect to the cross section. Pi over 4 times the change in diameter per length, z plus d naught being the diameter at z equals 0 squared. Okay, good. Now we're gonna, let's see if we can, we've got the expression, we've accounted for the variation in area with axial length, but our problem is asking for heat transfer, and the mode of heat transfer is conduction. We have we don't have any bulk fluid, okay? We're dealing with conduction in the axial direction. So for conduction, I'm going to be using Fourier's law. Good. And Fourier's law is going to tell me that the total heat transfer rate, Q dot, the total heat transfer rate in watts or in watts, divided by the cross-sectional area. Cross-sectional area being a function of z, is going to be equal to the negative k dt dx, right? dt dz, sorry, along the axial length. So that's my governing. This is the equation, okay? This is the equation that's describing the heat transfer phenomena. But okay, let's see if I can integrate this. So, all right, Q dot. Now I'm gonna leave Q naught as it is, and I'm gonna, for my cross-sectional area, I'll be substituting this expression. All right, good. So what will I get? After doing some algebra, I'll get 4 over pi times the expression itself, delta d lz plus d naught, good, squared. Okay, let me highlight z, okay, in a different color, z, all right, good. That's gonna equal negative k times dt dz. All right, so on the left hand side, now this right here is a separable ODE. I hope you guys can see. This right here is a separable ordinary differential equation. This is a separable ordinary differential equation. All right, and let's see, let's inspect, shall we? The heat transfer rate has to be constant. Why is that? Steady state. There is no generation. So the heat that is being transferred into a section has to equal the heat that's leaving. So there's heat transfer rate has to be constant, okay? Steady state. Heat transfer rate. So, all right, let's separate the variables. Let's choose a nice color. I'm gonna go very monochromatic now. On the left side, I'll just have negative k. K is constant, so that just gets pulled out of the integral. It goes from t1 till t2. And okay, on the left hand side, I'll be able to pull out this expression. So 4 q dot divided by pi times the integral from 0 to L of this expression, delta d over L z plus d naught squared. Okay, so you guys are more than welcome to use Symbolab at this point to evaluate this integral, okay? You can use Symbolab to evaluate this integral, but I'm just gonna play around with it just for fun, okay? So I can rewrite this integral so that the power is negative. Okay, I've rewritten the integral. Hopefully I'm not gonna make any mistake. Oh, and on the right hand side, it's just gonna be, I hope you guys can see that. That's pretty simple. That's a very simple result. All right, let's, in order to integrate, this is a definite integral. So you add 1 to the power. Okay, let's see. We're gonna see if I remember any integral calc. Add 1, divide by the new power, and the coefficient of your independent variable. Good. All right, I hope that's it. And this is going to go from the lower limit till the upper limit. Okay, upper limit minus lower limit. Of course, 4 q dot and pi are just tagging along. And on the right hand side, my conductivity and temperature are just chilling. Okay, good. All right, and up till here, I can pull out a minus sign. Okay, so I'll get negative 4 q dot over pi. And I can pull out this expression. Okay, this is going to be constant, and this comes out to be L over delta D. So I'm just pulling out the constant terms. And what am I left with? What am I left with? If I put it back in the 1 over form, in the in its original setting, and this is what it's going to look like. Okay, and this is going to go from L being the upper limit and 0 being the lower limit. Okay, and of course we have a negative sign on the left hand side, we have a negative sign on the left hand side and a negative sign on the right hand side, so those just drop out. Good. All right, so 4 q dot phi L divided by the change in diameter, this becomes, all right, let's see, I'm gonna be careful. If I plug in L, I'll just get d naught plus, d naught plus delta D. Good. And when I plug in 0, I just get d naught. All right, make sure I close my parentheses. Okay, and this is going to be as it is. Okay, nothing has changed here. So okay, what we're trying to solve for is the heat transfer rate, right? That's what we're trying to solve for. So hey, let's do some algebra, shall we? Q dot, the rate of heat transfer, is gonna equal conductivity times T2 minus T1. Okay, 1 by 1. Pi goes to the right hand side, 4 goes to the right hand side. Delta D, the change in diameter, goes to the right hand side. Hold up, let me make this more clean. Delta D, okay, T2 minus T1. Okay, make sure I don't make any algebraic mistake. That's going to be fatal at this point. Hopefully I won't do that. Fingers crossed. And then in the denominator goes this and that. Good. And okay, up till this point this looks good, but I'm just gonna expand delta D. Okay, I'm just gonna expand delta D out. Okay, I know that delta D is just equal to D2 minus D1, right? D2 minus D1. Wait, sorry, is it D1 minus D0? Go back, sorry. Oh, D sub L, D sub 0. Okay, so yeah, I'm good. I'm keeping everything under control. DL minus D0. And upon making this substitution, nothing is gonna significantly change. Nothing is gonna significantly change. You're still gonna have Q dot on the left hand side, and you're gonna have pi times D sub L minus D sub 0 divided by 4 divided by the axial length times the conductivity multiplied by the temperatures, the temperature difference at both faces. Okay, good. And the reciprocal of 1 over D sub L, D at one end, minus 1 over D at z equals 0. Okay, so this is your final equation. Okay, and up till this point you've solved the heat transfer. Now you can just use Excel, MATLAB, Maple, MathCAD, whichever software you fancy, and you can just play around with all of your parameters, conductivity, different temperature differences, the different diameters, and see how that affects your heat transfer rate. All right, so now, all right, I have solved the heat transfer. The next step is just plug and chug. All right, and yeah, so just to give you guys a quick recap, variable area transport. We did a simple example of conduction in the axial direction. First off, we started off by accounting the variation in the diameter with axial length, and then we used, and then we mapped, and then we took into account that that's going to affect our cross-sectional area along the axial length. This is my doodle. This is my nice, this is my okay-ish doodle. And area, okay, we had the expression for area, the variation in the cross-section area along the axial length. Good. And this is Fourier's law. Okay, keep in mind I'm not assuming constant area at this point. So upon integration, okay, that's a mess. I substituted the expression for area, and this right here, let me make this more clean. Sorry. Okay, so the bottom expression in the one that I'm boxing right now, that's the expression for the well, that's not the whole expression for area. 4 over pi is also hanging in there. So yeah, and then we just separated the variables. Once again, I'm emphasizing that you can use Symbolab or some symbolic math software to perform this math. Okay, use whatever tool you find reliable. Okay, I trust Symbolab. Okay, and if you use Symbolab, I think that's a good tool. And this is our final governing equation. All right, guys. So thank you so much for watching.